is going to give us a value of about approximately 26.24. We're going to have 2116 divided by 166 is going to give us a value of approximately 12.75. So this is approximately 12.75. Then we're going to have 289 divided by 167 is going to give us a value of approximately 1.30. So 1.30. And then finally we're going to have 17,689 divided by 167, which is going to give us a value of approximately 105.92. So that's 105.92. Okay. So this is our measure for our test statistic of how far each observation is away from the expected observation relative to the expected observation. Okay. So our test statistic, our chi-square test statistic, is defined to be, well, it's defined to be the sum of these squared distances relative to the expected frequencies. So it's the sum of them. So I need to sum up this column here. Okay. So when I sum up this column, I have 0.10 plus 0.29 plus 26.24 plus 12.75 plus 1.30 plus 105.92, which gives us a value of approximately 146.6. Now that's a very large test statistic that we have here. Okay, so we have it's 146.6. So in other words, what we have here is that our chi-squared, okay, test statistic is 146.6. Okay. So now what we need to do is, actually, I haven't actually specified the alpha value, okay, and we probably need to do that in here, which is the significance of our test. Our significance, okay, is alpha is equal to 0.05, okay? So I'm just assuming that's at a 5% significance level. In other words, if I do reject a null hypothesis, okay, I'm willing to accept being incorrect in that rejection 5% of the time, if that makes sense. Okay, so we have our test statistic. Okay, we've calculated our test statistic. Let me actually lay this hypothesis out again. Okay, that's probably the best thing to do here. Okay, so what we're going to do is we're going to have a look at, so the hypothesis, maybe I'll just write this down here. So here's our hypothesis test. We've just calculated the test statistic. Okay, so our hypothesis test, H0 is going to be that the observed distribution, is the same as our expected distribution. Okay, our expected distribution. The alternative is that they're different. That the observed distribution, okay, does not follow the expected distribution. Okay, the expected distribution, and don't forget the expected distribution being that everything is as equally likely as everything else to happen. Okay, that's the first thing in our hypothesis test. Part 2, I should have said, is the significance of our test. That's the probability that we're willing to accept with respect to incorrectly rejecting a null hypothesis. And what we're going to do here is alpha is equal to 0.05. Okay, then we have our test statistic 3, our test statistic. Okay, our test statistic is the chi-squared test statistic. It's equal to the observed frequencies minus the expected frequencies squared relative to the expected frequencies, and it's the sum of all of those across all of our observed, all of the I suppose the possible values that could occur in our discrete distribution. And in our case here, we've just calculated this to be equal to, well, we calculated it to be equal to 146.6. Okay, so that's our test statistic. Our degrees of freedom for this particular test is the number of levels of measurement associated with our variable. In this case, there's 6 possible things that could occur, and minus 1. Okay, so it's equal to 6 minus 1, which is equal to 5 in this case. Okay, now to calculate our critical values, part 4 is our critical values. And let's keep in mind that we're doing a chi-squared test. So this distribution, the test statistic follows a chi-squared distribution. Okay, so the distribution is the chi-squared distribution, which, depending on degrees of freedom, is a distribution that is skewed. Okay. Now let's just think about the properties of this particular test statistic. Okay. If there was no difference between the observed and the expected, okay, all the way down, in other words, the observations actually match the expected frequencies, if there was no differences between them, we'd expect all these values here to be 0. In which case we'd expect the ratios to be 0, and in which case we'd expect the test statistic, when we sum up these ratios, we'd expect the test statistic to come out to 0. So actually, a test statistic down here, okay, is a chi-square down here is evidence to suggest no difference. No difference, okay? The greater the difference there is between the observed and the expected, the bigger these values are, okay? So actually, a test statistic down here is evidence to suggest a difference, okay? A difference between our observed distribution and our expected distribution. Now we're setting alpha is equal to 0.05. So actually this is a one-tailed test. Maybe I should say this here. This